well. So I have some experience behind that. And also, what we just did with Rob Selim just now, I've been able to do with sixth graders using the DIY Harvard Smithsonian tool that looks very much like we just did, but much simplified, much more accessible. And it actually shows the FITS files as opposed to kind of like taking it by that. So it is possible to do.
I'm Louisa Rabol, and I wear many hats, but the most relevant here is I work for URSA, the Infrared Science Archive. So if you've used data from 2MASS, from WISE, from Spitzer, you've used data that I helped serve. And the other reason I'm here is that I run a program called NITARP, the NASA IPAC Teacher Archive Research Program, which partners small groups of educators with a research astronomer for a year-long authentic research project. And there's many NITARP alumni among you. I also wrote an article in a recent Physics Today, and for reasons passing understanding, they gave me a whole bunch of analog copies, which I brought. So if you'd like an analog copy, please come take them, because I don't know what I'm going to do with them.
Great. Yeah, I had Louisa out for a colloquium about a year or so ago, and she showed me all the URSA stuff, and we embedded it very deeply into our MW curriculum. It's not just optical and radio, but it's optical, radio, and archival infrared, thanks to her visit. All right, we're going to get started. Reed, give us a countdown clock. There we go. Yep, oh, he's already counting, so here we go. I wrote my questions kind of long, and so I'll read them out, and we'll hear from the panelists, and we're going to keep this show on the road, keep it moving. Okay, what matters more in Astro 101? This is my favorite question, if you haven't figured it out already. What matters more in Astro 101, skills or content? Learning by doing or learning the results of others doing? I'm not biasing the question here, am I? To what degree does this have to be a trade-off between breadth and depth? Are the gains in skills and in understanding and appreciating what science actually is worth the trade-off? So who would like to tackle this first? You got a shared mic right there.
I'll go give it a shot. So I'm starting to see already in the field a bifurcation between two different types of Astro 101. Like you have your classic lecture show of like comprehensive, and if the students are putting attention, ha ha ha, they'll get that encyclopedic knowledge of where all of astronomy is, right? And then you have show of the emergence now of a class that is very much focused now on the observational experience, right? So here what we're considering thing, I believe, is a gamble. It's a gamble, right? Because obviously you cannot be comprehensive and also teach the skills so they have that observational research experience as the Astro 101 level. So the gamble kind of goes like this. How about if instead of being that comprehensive, we focus on a set of very rich, in-depth experiences, very rich, in-depth experiences that are so compelling, that are so absorbing, right, that offers the challenge just at the right level, that they get hooked and they become lifelong learners, and whatever you do not cover, which you felt you needed to cover in the Astro 101, the students themselves will go out and seek those experiences and that knowledge in yourself, now having had the rich experience and the motivation for actually going in depth, right? So that is kind of the gamble. Now, is that the right gamble, right? That's the thing that we have to kind of decide as a community.
So I think that a lot of the topics in this question, and for that matter, your second question, we did already start to talk about this morning. And so some of the notes that I was making during this morning's conversation, I mean, yes, it's certainly true that there's a lot of the basic facts that kids could look up on their phones. But you really, and you had asked us to be provocative if need be, okay? So I think that they need to know enough. So if you're gonna ask them to calculate, say, the density of a Bach globule, they need to have the sense to back up and say, okay, wait, did the density that I just calculate, is that denser than a proton? True story. Or is the velocity of the star that I just calculated 4 times the speed of light? Also true story. So they need to have enough background to understand, to interpret the numbers that they're getting.
Mm-hmm. Yeah, whenever you do any
it's
calculation,
yeah.
the next question, was that reasonable? And they have to be able to answer that.
My notion on this has to do with what I'm trying to accomplish, which is in some sense deal with what you just said, which is for young people or for maybe college undergraduates in the last science course they're ever going to take. That really resonated this morning when someone said that. That may be your last shot, but getting people signed up to be lifelong learners, to understand and appreciate science. It's always sort of bugged me ever since basically the 70s that you started to see this anti-science or skepticism of science attitude develop in our country. And so that is just my thought on this.
And they don't know what it is.
Yeah.
It's a bunch of facts that the elites learn in college.
Astronomy facts are not as important as whatever you hear, whatever information you get from whatever, that you be healthily skeptical about it. You know, what is the noise in every data point that you receive in your day or watching the news at night?
I desperately want my doctor to understand error bars.
Well, and follow up on something I said earlier about this being data science. Look, there's something very interesting that we're doing here in common astronomy when we're analyzing these images and you're looking at very large data sets. Why? Because let's suppose you have a FITS file and you have a bad hot pixel or entire row or a cosmic ray and all of that. Does that mean that that image is useless or that the study that's based upon that image is invalid, right? Of course not, because we can characterize that error. We know where it comes from. We can control it. We can manage. We can still make something meaningful. And I think one of the things that we're seeing now in the culture is this, and that is that we have hacks out there that essentially take this extreme methodology to irrational levels and say, oh, you did not calibrate those I-scores through correctly, henceforth your entire study is invalid, henceforth the entire thesis of climate change is invalid, right? You have folks that are actually operating that level and the general public is actually buying it. So one of the things that potentially we could do when we're introducing this methodology and this approach of looking at large data sets is essentially really understanding where errors come from, how we manage them, how we understand them, and how we extract meaning out of these images in these large data sets.
There is a hot pixel in that type 1a image, and consequently, the universe is not accelerating, right? Yeah. Mm-hmm. And I think the only way you can combat that is to put people through the process where they actually have to do science and not just hear about it. And do the struggle and see that it's hard work, but it's honest work. And there are people, yeah, they'll occasionally get it wrong, but enough of us. Let's get the discussion moving throughout the room. Here we go.
I wish that was the case. I wish that was the case, that we could go through and say, here's the methodology. You believe this weirdo thing. I'm going to take example, the moon landing. I went to AAS once. And I said, hey, here's this Fox video that was on last year. This was a long time ago. We didn't land on the moon. And then I'll come back and they watch that while it's gone and I'll tell them, well, it's a bunch of bunk and they'll all buy into that. And that's not what happens. They come in and they bought into it. It went from 10% to 50% of my class thought we didn't land on the moon. And I could not undo that. And I went through and had them reproduce all the science. I did what we as physical scientists think are the right approaches, logic and data, and that didn't work. You have to go to social science. You have to go through and say, we'll do attack ad hominem, and it was only a Penn and Teller video that made the moon conspiracy folks look like they're just crazy cat people, which they did, brought it down to zero. That if we want them to buy into our science, we have to go beyond just skills and content and get them to be on our team. And I don't think that's a good idea. That's necessary. We want them to have little NASA stickers on all their laptops so that when it comes time to buy into climate change, they're not going to trust their political party. They're not going to trust their parents. They'll trust someone who actually had studied it.
An
And I
idea-
don't like that, but that seems to be what the data is showing.
What's the, sorry.
But I was going to say, an idea popped in my head. Maybe you go to your school's film school and get the film students and say, I want you to fake the video of the moon landing using the technology of the day. And maybe that's a way to approach it. I don't know.
What's really cool, though, is if you go into an Old Navy, you can find T-shirts with NASA logos. You can't get Old Navy T-shirts with Department of Education logos or Department of Energy logos. You can get them with NASA logos. We have to lean into that somehow.
Mm-hmm. More. Everyone's convinced on this one, then. Okay, we'll move to the next one. Oh, was there another? You got one? No, there's no stalling. We're moving on. Well, the second one I think we could do very quickly. To what degree, yeah, they are very similar. To what degree should we be using real database investigations to teach content versus more traditional lecture and lab approaches? I noticed these questions are essentially the same. So how about I throw out a straw man? When we teach, the traditional format is 3 credits lecture, 1 credit lab. And old school, the labs didn't really connect very strongly with the lecture. We've talked about this before. You go out with the 3.5-inch telescope, there's only so much you can do. You can't do the great debate of 1920, et cetera, et cetera. We're changing that now. We can do these things that are in lecture. What if we flip it around? What if the standard becomes 3 credits of investigation with 1 credit of lecture or recitation or wraparound to help bring the bare minimum background that you need to make the investigation more meaningful? Go for it. You got a mic right there.
3 times the data, 1 times the opinion. I agree with you.
Yeah.
No, we did that as part of Western Carolina University, and I like to thank the meanness of the administration who decided to do away with lab requirements for liberal arts credit, so you only need to take lectures and then you're done, right? So we tried to kind of play that and say that, okay, well, yeah, how about if we introduce this liberal art course, which is 3 hours, it shows up as a lecture, that's a requirement, but it's a lab.
Uh-huh.
Right, and we have to actually do this, right? So essentially, at this point, this is an example of 3-hour lab period, no lecture, right? But it doesn't quite work like that. But I still don't have it right. Right? But potentially that model exists.
Yeah, and with MW, that's very much what we're trying. The course is essentially a laboratory course with minimal lecture wrapped around it. Yes, here we go. Throw a mic.
Okay.
Yeah.
Yeah, so what we did, what we do at Coastal Carolina University, we do a variation of what Enrique was talking about. We have a 1 credit lab for our astronomy class and then the 3 credit astronomy class. But what we do is we make them co-requisites. They have to take them. I know other people do that. And what we do is we basically we meet twice a week or 3 times a week for Monday, Wednesday, Friday. And we just intermix the 2. So that way we're not bucking the system. The students still get a lab credit and they still, get the science class, but it's all mixed together. They get the same grade for both classes. So that basically gives us flexibility to mix lecture and lab on a almost daily basis in the exact mix we want. And it's a good way to do that without totally going to your college and saying, okay, guess what? Yeah, we want you to drop the lab credit, right? So it actually works very, very well to do that. And since we're actually doing it at the same time with the same instructors, it works really, really well. So, and it gives you the ability to totally change that balance to whatever you feel you need to do on a specific day. So just thought I'd throw that in.
And one of the total side point, and this is Rachel's work, but as you've already mentioned, self-efficacy, we see huge gains in self-efficacy from the doing approach instead of the traditional lecture approach, like off the chart, startling, publish in PR kind of thing. All right, others.
I want to throw in one other thing there because you've got two different modes of learning up there, right? That you're saying lecture and lab. But I've had way too much of my career involving history professors, and as a result, realize there's more modalities for learning besides just what we call lecture and lab. There's active learning and or engaged practices that what we wouldn't call labs. There's role-playing games. There is all sorts of other engagement activities you can do. And so I would encourage us, we don't have to replace all of the lecture with just labs. We could replace lecture, which is terrible anyway, other than proving them that you can talk, with other kinds of activities, because especially for our Astro 101 students, maybe some of them, the lab portion of it isn't going to resonate with their learning modality as a modality for their learning, but they might resonate with the role playing, or they might resonate with some other building skill. So I'd encourage us to think about other ways to replace lecture besides just lab, even though that's the easy one for us to go to as physical scientists.
That's a great point, and this is where we can overlap with politics and planning. And Michael Allen has a great exercise where you plan a Mars mission on a fixed budget, and you have to make choices. And they really have to think, oh, well, I'll cut this out so I can have that, but then you can't do that, or you can't eat, et cetera. And mixing science with policy through these kinds of activities.
So just maybe as a slight counterpoint, or not even counterpoint, but just an example. The C10 class at Berkeley, which is taught by Alex Filipenko, I just saw like really, really off the charts development of that sense of awe in students. And the number of students coming out of that class with a really profound sense of wonder about the universe and understanding of a lot of things based on the assessments at the end of the class. It was a lecture-based class, and we had, think pair shares during lectures. We had live polls during lecture. Lots of interactive demos that involve balls flying out into the crowd and coming back and all of these kinds of things. So not pure lecture.
Sure.
But the other thing about it is that, from the TA side of it, the reviews for that course were so high, like people's sense of enjoyment for a lecture-based thing. But down to the minute that class was planned, because Filipenko had taught it for so many years, he'd worked out this formula, which was, basically until maybe the last lecture, every word was sort of prescribed. And when we would have our weekly meetings, he'd be like, I'm 1.7 minutes behind on the semesterly schedule, right? And to the point, like it worked is my point, is that we had labs as part of the class that we would do in section. We would, measure spectra of tube lamps. We would go up to the observatory and measure, basic things in an observation lab. So there was a lab component, but I guess the point I'm getting to is that even that very traditional lecture format with the right huge amount of experience and effort over time did manage to get itself into a place where it was the single most popular course in the entire campus.
Sure.
So there is, elements I think that are not worth abandoning. And again, too, just crazy how much content he could cover. With the class planned down to that level, there was a lot of content that students learned, and they seemed to take away something from it, at least based on their ability to take the exams.
Yeah, I think about this a lot, and sometimes you can have an amazing lecture and they walk away, that was great, and it gets very high scores. But what about other measures? Sure, you can design these things where the pre-post contents are great, but we go 10 years later, you run into a student 10 years later and they remember something from your class, and you're blown away that they actually remembered one thing that you taught them 10 years ago. And it tells us kind of where our expectations are. I wonder how, not any specific course, but this kind of course that's super popular, how does it affect the affective measures, self-efficacy, attitude, career intention. Sometimes you just have an amazing personality, and they're like, I love that class, but 10 years from, did it create more STEM majors? And when you say planning down to the minute, I think the key phrase here that we're talking about with these investigation type approaches is uncurated data. If you can get to the point that your students are working with uncurated data, which is say another way, if you can get to the point where you can work with your students with uncurated data, I think that's where the real magic can happen. But boy, it's a big lift as well. Just to counter a little bit the guide on the side, sage on the stage argument. You got a box?
I got a box. I think that what you're saying too is also to remember that we have to ground ourselves in what cognitive research is telling us about how people learn. So we know people will learn if they're enjoying themselves. We'll also learn if grossly embarrassed, internalize something. We don't want to choose that one. And we also are able to learn if we're able to chunk things in fact bundles. So facts, knowing some stuff like what those dang error bars are for is helpful. So in order to learn, and that's just a couple of examples of how, as we make choices, we have to think about how do people learn.
I think we should run with that middle point and stop everything else at the conference and focus on embarrassment learning techniques.
I think we also have to ground ourselves in reality. The class he was talking about too had probably how many hundreds of students in it?
Like 900.
Yeah. I mean, 900 students in it. How much? When you're talking about doing investigations and things.
Challenging. And the seating.
And the seating and things like that, that's a reality. I went to University of Michigan. There's a class similar to that. That's one of the favorites on campus. It's actually been in the news several times, called Extreme Weather. And the guy who did it and everything, he uses all this technology. The students are engaged. It's a 500 student class. The students are engaged most of the time. They come in, they have the computers open. What they're saying is popping up on the screen behind them. So they can ask questions while he's lecturing. The whole they're doing things. So it's an interactive lecture.
Yeah.
So, but it's 500. There's a difference between sometimes, I'm at a community college, I teach much smaller classes. So there's a difference in just pure reality too.
Sure.
So I think that.
Yeah, and I don't mean to put it down. I spent 15 years or more teaching 300 at a time. I love doing it. But in recent years, I feel that it was more for me than for them. Edutainment, it made me feel really good, but I don't know if they really walked away with what it takes to become the next generation of scientists or to be STEM educated, literate, and productive citizens. I don't know. I feel like I may have wasted a good chunk of my life, and so I'm trying to learn this other stuff. But anyway, more on this. Shall we keep going? Because Calais is starting to get happy, because I'm only in question 2 here. Okay, number 3, science is much more than science. It's communication, it's writing, it's writing both formal and informal. That's something I've focused on recently, informal writing in my MWU class. To what degree should this play a larger role in how we teach science? Or do we just give them problem sets? Let's hear from the panel first.
Going to give it a shot. I think that this is one case where potentially we could be informed by essentially cultural astronomy and cultural non-Western traditions of astronomy, in the sense that that information comes to us in the form of oral knowledge from various cultures, and those are encoded specifically in narratives, right? So there's something about a narrative arc that actually helps people remember. And when you think about the things that we're asking the students to do, we're actually asking them to associate an entire complex of ideas all together in a bundle. One of the things that I did when I was new in teaching in a small liberal arts college is that the final exam was essentially an essay, set of essay questions. But the study guide for that kind of went like this, that I would come to the students and I would give them an object. Their job is to actually trace the history of the matter of that object to the Big Bang down to this very moment. So these objects were cup of water, it would be a nail, and I forget what the third object was, right? So if you have, say, a nail, at some point you have to talk about supernova, right? As well as essentially the origin of the solar system and things like that. They needed to be able to trace that as kind of like a chain. So potentially one aspect of this, in terms of what we call informal writing, would be to do that narrative thing, because essentially, if what we want them to do is to be educated citizens and actually have a presence to teach science to children, right, to the general public in informal settings, then that narrative aspect might actually be an important part.
It seems to me that the most difficult thing with younger kids is getting them to write up a result. There's something developmental around 8th or 9th grade where you start to be able to do that. So I think the idea of writing to describe what you've learned is really important. And it doesn't have to be formal writing. It could be a simple essay or even a paragraph on an email to a TA. But it's playing back the ideas. It strikes me as a really critical skill for life.
Yes.
And writing up your experiment or your results seems to me to be a very important thing.
It's what we do every day. And we do informal writing, informal communication, much more than formal. Occasionally you sit down and write a formal paper. But most of the time, even if it's to your colleagues, your peers, it's informal writing. When they go to do that job interview, what did you do in this research group as an undergrad? They need to explain it to a non-expert.
It's definitely critical, absolutely critical. And the teachers that I encounter, even the teachers, not just the students, but the teachers, they're so used to the subject matter being siloed. You do math in math class, you do writing in English class, you do science in science class. When I encountered them and I asked them to do these things together, they're like, what? And the number of times I have had to explain, no, it's science writing. That doesn't mean it has to be passive voice. The number of times I've had to explain that, oh my gosh, yes. And yeah, exactly. And then on a separate note, when I was in grad school, when we were TAing for one of the survey courses. Now, admittedly, this wasn't one of the courses I was TAing. The kids had been complaining bitterly for 2 out of the 3 quarters. Oh, you're making us do math. We can't do math. This isn't our subject. The professor was like, fine, write an essay. Guess what? They can't write either. So it's, definitely something for
They
those.
don't read either anymore either.
Yeah,
It's
exactly. But that's
videos.
something in the context of, I can't do math. Fine, write something.
Right. I'll just make a comment then off to you, because you had your, in our MWU course, we have like 30 educators who, funded by DoD, helped to develop this course and are finishing it up now. And we discussed this at length, and we came to the conclusion that their work product will be an astrophotography blog. Now, again, astrophotography is just the hook. Out of every astrophoto they make, they're doing deep science, Stromgren sphere calculations with temperature measurements from different emission lines, et cetera. But we settled on a blog format and also a vlog format near the end, where they take this thing they're so excited about and they explain it. And sometimes we then say, okay, now do a simpler one for social media, because that's where they post most of the time anyway. And so learning how to explain it to their peers has become an integral part of the MW course. Flip side is the grading is atrocious. Is May here? Good, yeah, I've been hiding from May because I think she wants to kill me after TAing MW. But you were next, I promised.
Something I thought of when I saw this question was communication really is important, especially as a teacher, because whenever you're trying to get a point across, you want to do so in a way that is respectful to the person and does not treat them as if they are dumb or, insert something derogatory, because we're all human beings. And just because we come in with misconceptions or different life experiences or different insert whatever, that doesn't mean we deserve to be treated not well because of the way that we think. And I feel like that's something on a whole that our society has lost in the way that we treat each other. I mean, look at the last couple of election cycles and the way that both sides of the aisle have treated each other. And if we are not setting an example that way, how are they going to come to trust us when we come with new data in whatever area that we are in and take us at our face value?
Respectful communication, critical. It's a lesson that this country's forgetting. Grab a throw mic. You gotta have a throw mic. This one's, no, I'm still alive. Throw mic. Closest throw mic. There it is. Go for it. Long shot, long three. It's a three. Oh, you got one. Okay.
Oh, sorry. There you go.
Oh, sorry, I didn't realize you. I was just gonna speak to your comment about people don't, or students don't read much
Yes.
either. That's definitely something I've run into in my classes, right? If you write a question that's more than one sentence, it won't get read. So I guess I'm posing an additional question on top of this that's related. I haven't figured out the answer to that. Is like, I think that is an important skill to learn, right? Just like the writing, the reading, like the comprehension of a question that's a few sentences. But I haven't figured out how to encourage them to do that.
So I write a lot of lab manuals, and I've learned over recent years. I actually started the semester before the pandemic. I'm very fortuitous. I turned everything to YouTube videos. I'm now teaching on YouTube 28 out of 24 hours a day. So I got a good rate going. And I have a great research team, and the results are consistently, they love the videos. Now that more years have advanced, the videos are too long. They now need to get shorter. But but how to deal with a multi-part question, I don't know what you do.
Yeah, so my students do a lot of projects, anywhere from 1 to 4 projects per semester. And of course, ChatGPT rears its head. They don't learn how to communicate. They communicate to ChatGPT and then give whatever good or bad results that ChatGPT gives them back. One thing I'm thinking about in next semester is to add discussion forums, which are over current events, that might encourage them, because they're okay with informal discussion, it seems. Like they text all the time, they post on social media all the time, and if they can communicate science in that same way, it's not a replacement for formal writing, but it does check the informal box there.
Okay, Calais. But no, don't give it, she's just trying to slow me down. Give it to Jonathan.
So I wanted to give a push for the actual problem set and the actual lab reports. I know you sort of dismissed them as, well, you just do problem sets. But if they understand that in order to do a problem set, that is communication, and that that they're learning how to technically write, and that's different than the informal, they actually write, do a problem, explain it along the way. And if they don't, then I guess they don't get good grades. And maybe after a few iterations of that, they kind of figure it out. Then you're teaching the right, but you're also doing something somewhat traditional.
Crickets. No, I'm always teasing Jonathan. We're butting heads. He's old school, new school.
Oh yeah, I also hate his videos. They're awful.
Yeah, he hates my
They're
videos.
fine if everybody's at home watching them. They're terrible if I'm trying to teach something in class.
Yeah, because you got 20 students playing, my head's on all their cell phones while you're trying to teach.
Yeah, I've got my,
I know, it
exactly.
pisses you off. I
want
love
my
it.
students not to
Who's next? Let's get a, here. Oh, you were closer, so you can
So in high school, I was the art and theater kid, and my history science teacher, I love science as a topic, but I never saw myself as an active participant in science. And my science teacher would tell me, you need to go into science, and I didn't believe him, but he would get me up to draw models on the board for him and help explain concepts visually to other students in my peer group. Fast forward a few years later, I got a job at DHEC, the Department of Health and Environmental Control, that didn't require a degree. And I learned that there were so many different ways to contribute to public health, which is another scientific field, through art and writing materials. And I got to interact with so many science jobs that weren't sitting doing what I thought was science. And then a year and a half later, I enrolled for my science degree. So I think it's important to give people an idea that they can contribute to the community of science and the body of work that we do that isn't necessarily always, working with data or always working with math.
I always tell my students that words matter more in science than they do in English class. In English class, you get to describe a beautiful picture the way you want to. You can say the beautiful, you can describe a scene the way you want to. But in science, words have to be very specific. You have to be very specific in your words. And my PhD thesis advisor was a stickler for the words, right? I'd be like, well, the substorm. He's like, the what? The isolated substorm. It wasn't during you probably have no idea what I'm talking about because my field's different from astronomy. But he was very specific. And I'm like, you can say the cerulean blue sky, but here we have to say something very specific in science. There was friction. Well, what type of friction was it in the lab? Are we doing a static friction? Are we doing kinetic friction? What type of friction? Did you prove that? No, you didn't prove it because science never proves. And I have to be very careful in my school because I have a lot of international students because I'm in the DC, Baltimore area. And I have to remember that there's a big language barrier. And so I have to work a lot with when they're turning in their lab reports that I'm also working with that language barrier. So a lot of times I'll circle it and I'll try to help them with their wording and things like that. But I always tell them in science, words matter more than in your English class because you have to be specific. You have to tell them exactly what you want to say.
It's more challenging, and in many ways, you have to be more creative.
Yeah.
In the arts.
I used
to do science.
When my husband and I first met, we met in grad school, and he would write, he was an English minor. And I'm like, you have to stop writing like a pompous ass. Because nobody wants to sit down with a dictionary to read your paper. Because don't use 5 adjectives for something when you're just trying to tell them what's going on in your data. You have to be concise, and you have to tell the reader what you're trying to say.
Okay, keep the next few points quick because we're moving on soon. Go for it.
Hello. One of the things that I do in my intro to astronomy class is, and I've done it 2 different ways now, is I started out with discussion boards. And what I have them do is every week they have to summarize a news article. It doesn't have to be long. I tell them page and a half. That they're not writing a page and a half, they're only writing a paragraph, but they're summarizing something they read from NASA or Sky and Telescope, not date and time or photo of the day or press releases, but something that is of value because there's always something interesting going on in the astronomy community. And with the discussion board, I like it because then you can comment and they can comment back and forth and points for that. That's a much harder way to grade than to do it as an assignment. So I'm still working that out, but it gets them writing and to just communicate. And, they don't have to write it. Like the hardest part is to keep them from just copying bits and pieces from the article itself. But if you can keep them from doing that, and you can usually tell based on the spelling whether they wrote it or not. But that's something I do, and I like it because then they get excited, and some of the students tell me that's their favorite part of the class is, oh, I didn't know this, or look, they just found such and such a thing, and they can share it.
think you were next, and then we're probably gonna, unless, was there, and then you, and then we're moving on to the next question.
This on?
Yep.
Yes, okay. Just a pitch for the reading part. Google Scholar. A
Okay, let's
portal.
switch to this one. For whatever reason, I'm having a tough time with that one.
Better?
Yes.
Eat the mic, right? Yeah. Google Scholar. So, and I think it's really important students see a portal to where they can get real knowledge. That's not Wikipedia, that's not Newsweek, it's not the web, whatever. And then see who's doing the work and how. And then also absorb their writing style and learn that they can just read an abstract and go look at the figure and they don't have to read the whole paper, for example, right? But then easily, trace citations and get a sense of the field. So I think that's a real important skill that they have, to see that there's more scientific information out there, whatever science course, but at the introductory level, even in a 101 Astro, if they can get that lesson and realize that there is a place where they can find truth and not opinion, and actually see it and read it. So I'll pitch for that.
You don't even need Google Scholar. You need ADS, Astrophysics Data System. They're about to change its name, but that's all of astronomy literature from the 1800s through this morning, all indexed. There's also something called AstroBytes, where graduate students take a current article and summarize it at the college level. So Google both those things, or when I come back to my computer, I can give you the links.
I'm aware, but Scholar is a general tool for whatever they do.
You'll be next. I forgot Clay.
Yeah, this will be quick. Well, there's two things. First, one reason I think students have such trouble writing is our fault. We assess it so badly. It takes so much time, so much more than most of us have, to really engage deeply with what students are thinking and help formulate ways to make them express it better. And I struggle with that lots and lots. And to your recent point, the one of Dan's articles that he wrote, I was actually going to, like getting inside students' head, like understanding how to assess writing, evaluate writing, think about writing. He wrote an article about astrology. I'll just,
To the MedCrave group.
for the, right, I'll just throw that out there, Google it. Google Dan Reichert MedCrave and you can read it. And the point of it is to help students understand how to evaluate writing, how to evaluate other writing, how to evaluate other communication. And it's been illuminating for me to give that article in my class without explaining its.
So they know every sentence is a common logical fallacy or pop culture reference, and the journal still approved it.
Yeah.
So Clay gives it to her students. Most of them.
They take it at face value. And even when I ask probing questions designed to elicit their understanding that it's not a valid article, they'll do calculations correctly, but not come to the overall conclusion that the article has some serious problems.
It's now been cited in a published paper. You were last, and then we're gonna move on to the next question.
We'll try this, one of these speakers, but glad I got to kind of wrap this up because I have actually a few anecdotes to throw in. First off, when I read this question, when you sent it out, I think the question maybe is phrased wrong, because the answer to the question is, duh, right? I mean, of course communication is important,
yes.
Right? And what we're doing right now is communication. And what this conversation has been is more like, what are the challenges we face to communication? And the anecdote I wanted to provide, one of the anecdotes I wanted to provide was, in fact, I'm raising a scientist, so to speak. My son is in college at Asheville, and he's studying environmental science. And I have always, and he's going to graduate in December. And I've always emphasized writing. And to the point down here about how English, as a former English major, you have flexibility with your words and you can describe and you can make your own point as long as you can sort of validate it. He actually says he hates English for that very reason.
He likes science and he likes math because, you're not necessarily math, but he likes, what he does because there are definitive answers, or he's searching for a definitive answer anyway. So it's kind of funny that you mentioned that. He's like, he doesn't want to express himself. He wants definitive answers. That's the scientist in him. But I've always emphasized to him, well, you still need to have a good writing background, because no matter what you do, no matter, and this goes for majors, non-majors, anyone, any student, no matter what job you have, you're going to have to communicate. If you're flipping burgers at McDonald's, you're going to have to communicate with people, right? So it doesn't matter what you do, you're going to have to communicate. So that's the first thing. And then I have a daughter who's going to graduate high school next year, and she's very much not science and math. She's an artist. She's all, and I have emphasized to her, well, there are many avenues for art. Art isn't just, drawing in a sketchbook. There are many technical jobs and many ways to communicate through that. And in fact, one of the teachers at her school this past year, her science teacher was originally got her MFA in visual design, and then went on to become a science teacher and graphic designer. So communication, and to the last point about math being a form of language, that's a great analogy. I never thought of it that way. So the point through all this is just that we're going to have to communicate. No matter what you do, every student in the world, every person in the world communicates in one way or another. So it's not about whether we need to emphasize communication. It's what the challenges are and how we emphasize communication.
I mean, we're all here because we figured out how to do science and writing and communication. If we didn't figure out both parts, we wouldn't be here. And the same goes for our students. And we can't leave it to the English department to teach our students how to communicate in our field. We have to figure out how to do it ourselves, even though that's not our formal training. But we've succeeded at it, or else we wouldn't be here. All right, next question. We're gonna plug along. So number 4, all of these skills matter for the 0.1% of students becoming astronomers. To what degree do they matter to the larger number of other STEM students? To what degree do they matter to the even larger number of non-STEM students? Over to our panelists. And if you want to take it, or you find the question boring.
No, I'm just going to just echo something that I said earlier in the day, and that is that data science, right? If we are going to, if the students are going to grow up and they are going to have to rely on large language model tools and have to be consumers of data that's based on essentially huge, extensive studies, then they need to acquire sort of a vocabulary and a sensibility and a recognition of what is the strength and value of analyzing and extracting meaning from those observations. So I would say that. So I'm actually very candid with my students, and I tell them, look, we're going to be doing all this robotics telescope stuff, but your value, your particular value for whatever career path is going to be is, we're going to be doing data science, you're going to be looking at average, you're looking to try to make meaning of data sets, including tens of thousands of possible different values out there, like, for instance, Gaia data releases and whatnot. You're going to have to make meaning out of this stuff because you are consumers of information. All of these studies having to do with vaccine efficacy are based upon similar types of approaches. So if we can instill that sensibility to them, I think that we are doing a service for our students.
I'd generalize it even beyond data science. Just authentic investigation is something that's in common for all those groups, whether they're going to become astronomers or other STEM practitioners or non-STEM people. We want to understand what science really is. Data science, yes, and authentic investigation is something that works for all of them.
Yeah, I had similar notes. I mean, the notes that I had said something along the lines of establishing everybody's science identity, establishing their personal relationship to science, to scientists, to understanding that not all scientists look like middle-aged white guys with bad hair and a lab coat, understanding that that science, I mean, nobody here is wearing a lab coat, right? And I bet that no one here wears a lab coat to work. right? I mean, yes, there are some astronomers that wear lab coats when they're building instruments, but that's a minority, right? And I'm pretty sure that only the astrobiologists have test tubes, right? So I mean, the fact that the feedback forms that I get from the teachers and students, even the teachers in my program, say things like, I had no idea that astronomers were young. I mean, that's a big deal. That is a big deal. And so establishing a personal relationship with the people in astronomy and their personal relationship to science, to the data, I think that's pretty important because it makes science less magic. It makes it less obscure. It doesn't completely solve all of the issues with educated citizenry, but it starts. It starts to chip away at that iceberg.
You're good? Okay. Anyone else on this one? I don't think this is a super deep one. Comments? Yeah, Mike. Comments? Anyone else? Here we go, back here. You got to throw Mike somewhere in the vicinity. Someone's hoarding it.
And kind of like going off the idea of magic, I think a lot of times when we talk about, strategies for learning, we talk a lot about, oh, how are we going to let the students learn? What are they going to take away? I think we often forget about the sense of like why a lot of us are here in the first place. And for me, that was like awe and wonder. It is so cool that we can sit here today and say something about something that is so big and so old. And so to what degree do the skills matter to the larger audience? Maybe they do. Maybe they'll come back to it 10 years from now, or maybe they won't. But I think it's still cool that in a lot of the times you sit in a classroom and you get to learn about something you've never heard about before. And oftentimes you get to see the teacher there and they also get excited because probably they're there because they like the field. And that enthusiasm, I think, is contagious. I love taking classes, and I might be young and naive because I'm still a grad student, but if I could, I would just take classes forever. So yeah, I think this is an important question, but a part of it is like, well, who cares if it is relevant directly or not? If you're having a good time, isn't that also worth something? So, yeah.
I couldn't agree more. The awe factor that astronomy somewhat uniquely provides and the inspiration, there's so many ways to kill that. And I think so many of the ways we teach destroy that. And for me personally, the most memorable thing was in high school, the stupid experiment with the ticker tape, right? You have something on wheels, ticker tape behind that's punching and a
For the
weight.
Millikan oil drop experiment.
Yeah, I remember Millikan, but for this one, this was important for me because you could take data, you could plot it, and you have a law of nature. And that just was amazing that you can do that. And again, it's an investigative experience, at least for me, that was meaningful. But yeah, there's so many ways you can kill that inspiration. Others? Yeah, I denied you previously, so here you go. Probably.
Thanks. Something you said about Ola, thank you, reminded me of something that I've also known, which is that there are some programs that definitely train people for jobs, but for the majority of the time, we're not doing that. I know I talked to someone who owned a small business, and he was like, the first 6 months of an employee are a gift to them because they're not producing yet. They don't know how to do the thing yet. So one of the things I realized about my Astro 101 that I tell my students is you are learning how to learn. You're learning how to be more capable. You're learning how to become and show the world that you can do more.
Last bit? Absolutely. Don't want.
I do. I'm good. I'm good either way. Yeah, everybody here, we are a horrible bias sample.
Yes.
We are the worst selection effect that exists. We love astronomy because it was interesting and its awe and its sense of wonder. And anybody who is taught, at least if there's a certain point in time in the class where, especially in the beginning, years ago, back when I lectured more, I would get to this wonderful lecture on cosmology. Why do we need this? How's it going to help me? How can I make money? What's the point? That's the connection. And so This question here is very important because it's what we should all be asking ourselves when we plan our classes. You know, how do we teach things that are important to them in the future, even if it's not necessarily what it is for us? Now, what now I do is I sort of emphasize practically every day. Oh, the purpose of a Lord's curriculum is for you to learn tangible skills and learn something totally fascinating. And if I say that enough times, maybe they'll think it's totally fascinating like I do. But if we're not teaching them something that they're going to use in 10 years, we're wasting our time.
Just a little side note about these classes here. A lot of people come in on the bottom of these 3 questions, but if you do it right, they can transition to the higher levels. And so, you know, one of the tricks is satisfying both at once. Okay. Oh, we got to catch. There you go.
Hi. So Dan is right. This question is not very deep. I can answer it in 10 seconds. First question is somewhat. Second question, not as much. But I think it gets at a challenge that we've discussed in this room throughout the day, is that we are teaching astronomy in many different settings and many different modalities with very disparate audiences, students who are STEM majors, non-STEM majors, who have very different levels of prior knowledge coming in to our classrooms or into our places of learning. And I think that one of the ways that we can address that is, we talked about STEM identity and how that's really important throughout today. I think highlighting career paths within astronomy and within STEM is really, really important into building that STEM identity. So if you start to highlight STEM careers and a student says, oh, my uncle who is a welder has a STEM job. He has that connection. Then they can start to see themselves in STEM more. So I think that's really valuable for our non-STEM students.
Okay, we're one last, and then we're going lightning round. Or was that you? You want one?
No. Tony had his hand up for a long time.
Okay, we'll hit you in just a second. First, Lee. Here you go.
Yeah, I think is so the learning astronomy, it depends on the learning outcomes purpose, right? So for example, somebody need a presentation, so we can put a presentation, PowerPoint presentation, skills, knowledge over there. Then somebody learns something very fundamental analysis, so we can integrate analysis of scale in astronomy courses. And in my situation is we try to use astronomy to interest those students in the future, so they're interested in chemistry, physics, and everything. So for example, my colleague developed one small project, so use a telescope, spectral analysis to find out, so what's the components in atmosphere for Saturn and Jupiter, right? So the students get a first-hand data, so they can interest them. So in my opinion, it depends on the purpose, depends on learning outcomes. That learning outcomes is not 100% students take astronomy courses or 100% become a future professional astronomer. But it's fundamental training, fundamental learning outcomes to interest those students. Thank you so much.
Thank you. And Tony, for the last one, for this one, then we're going in lightning mode, because I don't want anyone to catch me.
I thought what Jonathan said earlier about us being very biased was appropriate. And I was thinking something that might be helpful for us to recontextualize this, because we're asking ourselves about teaching astronomy as astronomers, but I think it might be helpful for us all to think about something that you have learned or some class that you were in that you are not any good at, right? I tend to think back to like if I'm playing basketball, which I don't play. I'm terrible, and it hurts physically to throw that. But I'll still go to a basketball game, once or twice a year. I'll go to a baseball game and eat the hot dogs. I'm terrible at baseball, right? And in the process of doing those things makes me hate it more. But sometimes just watching it, enjoying it, like the lecture he was talking about, makes me think it's good. We need to think about these non-STEM people as not us. Like they, so how do we have them interested and to learn about something, but they might not, that 0.1% might be capable of becoming us, and we shouldn't be dissuading them, but making it something that they have a learning, enjoyable experience and don't get dissuaded. If I end up playing basketball and I throw my shoulder out, I'm like, I'm going to hate basketball even more after that. And so that's a delicate line. I don't think that having them all do exactly the same kind of research that is good for that 0.1%, it might actually be harmful in the long run by making them say, oh, I don't like this is terrible, versus finding the skills and activities where they come out of it and they're like, I was successful and or enjoyed that.
I agree. It's all about finding a challenge that's appropriate to their background, where having overcome that challenge, they can feel good about themselves. Yeah. Anyway, next question. Okay, number 5. And this is a good one. Modern science is highly collaborative. To what degree should this play a larger role in how we teach science beyond, for example, think, pair, share exercises? What about at the introductory level? Panelists.
So this is really, really sticky. I don't know about y'all, but I spent a good chunk of my pre-college education career being the only person who did any work on group projects. And by the time my youngest sister graduated, my mom tried to start a group called Parents Against Group Projects. Okay? I'm not sure things have changed that much because my son is still frequently the only person who does any work on his group projects. The major sea change, though, is that now, as part of his group projects, he has to turn in something that says what fraction of the project that his teammates did. So this has to be done, and contrast this with on the teams that I run, the feedback forms, everyone's like, this has been so awesome to work on a team where everyone's working and everyone's pulling in the same direction and nobody's sabotaging and nobody has fallen off the wagon. So whatever you do here, obviously modern science is collaborative, and I completely agree, it is a lot of fun to work on teams when everyone's pulling in the same direction, because that's what I do now, and that's awesome. But how do you manage that in the freshman or sophomore of college context? I don't know what the right answer is, because when I was a freshman or sophomore, I would have resented being put on a team in which I anticipated I would be the only person doing any work.
That's a great point. I hated being on teams too, but I've seen beautiful things happen when it works out.
Now, Dan, you modeled for us earlier when you asked us to essentially do astrometry of trying to generate a plot of distance versus time for this in small groups, right? So essentially you modeled for us crowdsourcing, right?
Yeah.
And I've done that in my class. As a matter of fact, it's been challenging enough that I actually approached the IT department in my building to figure out exactly when it's going to be the peak time of usage so that I don't overwhelm folks with all this crowdsource activity. One thing that I do in my class, so I've been doing flipped classrooms as well as active learning now for a decade and a half now, things like Think Per Share and lecture tutorials and all of that. So by the time that the students are already working on Opus Labs, we already created a culture in the classroom essentially sharing. But to address specifically what Luisa just mentioned about essentially the one person that does all the work, right? When I group students to work together in the labs, I group them based upon zone of proximal development, meaning that I use their previous lab scores to figure out where they are so that I can group them based upon that so that they are going to be roughly in the same zone. So there's not going to be one person that has an overwhelming set of skills to do that. Now, the thing about this is that there's still some resistance there. So I actually give them the option and that flexibility of saying, well, you could either do this lab all on your own and you have to do all the work yourself, or you could work in small groups. Some students do thrive, right, and have a meaningful learning experience if they share the work and they have that collaboration, because they need to voice their own concerns and thoughts about the process behind that, and others are just going to do poorly. So maybe offering that flexibility to students is what we're looking for.
So, in MWU, we build around a team concept, and it mostly works, though sometimes you have Not one person doing all the work, but one person who didn't do the work. At my Green Bank experience, it's different. These students are just, they're selected based on enthusiasm. But what I find there is the group work is really, really important because you can do team building, team bonding, and team belonging. And that's such a critical pathway, I think, to STEM identity. So if we can find ways around, oh, this person did all the work or this person didn't, and you form these teams, like in MW, they have team names and we make stickers and we have competitions using Kahoot, and they're screaming and cheering, and you build that kind of team bonding. It leads down that path to STEM identity. You gotta be careful not to get into the scenario you mentioned.
The collaboration thing was something I learned. It was one of my favorite things, non-astronomy physics, that I learned as a student, because, we were getting these hard level things and we're just like, sometimes we're stuck on where to go, but because we had started, just having a ton of classes together, we realized who was good at what. And so in a way, we became like professors to each other. In fact, we would even jokingly call each other Professor So-and-so when they were the one, showing, what, how to do a problem. Allowed us to prioritize and strategize, hey, we know our professors are at X time, and we know this person is available. You go ask the professor, and then aren't able to go to that office hour. And so it taught me that your professor can teach you, but your classmates can also help teach you as well, and to see that you have more resources than what initially you think you have available.
I'll just add to that. When we do the MW, this one's losing its battery, but when we do the MW course, we start with a skills self-assessment, and where they order their skills. So no one's saying I'm all great at this or all bad at that. They order them 1 to 9. So everyone, you don't know who's good or who's bad, but they say, some say I'm good at math, I'm good at science, I'm good at Scrum, I'm good at digital art, I'm a leader, or I'm good at organizing, or et cetera. And then they form their teams trying to get as many people high in those categories, and we reward them. Everyone has something to contribute.
I guess I haven't actually done that, but that actually sounds, that's what I'm thinking about in terms of, I can really see the value of, particularly if you're talking about, the class for non-majors, and you're having them do a science experiment. There are going to be some of them who are better at various parts. And I can imagine they will also be more likely to succeed group where they use those skills, and somebody's strong at this or that, or they have somebody directly that's part of their team. I can see real value in that. I mean, I went to college in the Jurassic period. You just kind of did it yourself generally.
Yeah.
But I certainly saw when my son was in college, these groups, and they put things together in presentations, and like, dear God, that would have been useful to learn at that stage. So,
Professional lives.
yeah, it would have been so fabulous to have that experience then.
People hate it, but we have to do it. And so, any comments on this, or shall we tackle? Jonathan, I'll give you 30 seconds.
Okay, I just want to say that this has been studied a fair amount in the scientific education literature, especially by Heller and Heller at Minnesota. When I was in grad school, we had taught the students how to work in teams and all these things. And if you take the time to be proactive about it, you can teach them how to work in teams. On the other hand, it takes a lot of time because you have to make that a goal of yours. And the other thing is, most of the things students present is having their grade depend on the bozo in their class. And so one of the ways you get around it is by having random teams every time. So that everybody has to work with somebody else. And then by the end, then you can let them pick, because instead of picking their friend, they'll pick the person who's going to work. I use cards.
Actually, I'm not going to try another question, but on the thing of teams, one thing I do at my summer program at Green Bank is, we have 15 projects, and each person signs up for 3 teams. And so they end up on teams with each other. I'm in this team the whole time. Everyone's on all sorts of different teams. And in that, you get not just a sense of team bonding and identity within the team, but across the entire cohort. That's you said random teams. Get people mix in every single way. They bond not just as a group of 3 or 4, but as that's even more powerful.
I also cheated my
It's very important to mix people of different backgrounds, et cetera, to make it. We're at 0, so we're done. So just a couple, round of applause to you all for a great day of discussion. And I'm looking forward to hearing back from you whether you like this format.